Welcome to another Algebra 2 lesson, and today, properties of logarithms. We talked about logarithms in the sense that we've used them, we've solved logarithmic equations, we've converted things to logarithms and stuff like that, but how are logarithms used? You're going to see two examples today. One where it's not used anymore in the sense of how I'm going to show it to you, but was very useful before calculators. And another one is how we measure different things on logarithmic scales, where a factor of 1 doesn't mean it's going up by 1, but it's going by multiples, like 10 to the first, 10 to the second, 10 to the third, but the scale says 1, 2, 3, called a logarithmic scale. We'll talk about a Richter scale when we get to that. But I want to show you this. What you see here is a page from a logarithmic table. What a logarithm table is are numbers converted from logarithms. For example, to read this, if I want to know the answer to this question, 10 to the what power would equal 1.47. Okay, so I look down here, I look for 1.4. There we go. Then I come over here and look for 7. So 1.47, if you follow along, so it's about 10 to the 0.167. Now, why in the world would we do that? Why would we convert all these numbers to logarithms? Right. To make calculations easier. That's really the gist of it. Let me show you. We're going to take a not very complicated equation. Or, I'm sorry, expression to multiply. Just going to multiply these two numbers. You know how to do it. You've been doing it for a long time. 3 times 4 is 12. Carry the 1. 3 times 1 is 3, and 1 is 4. 2 times 4 is 8. 2 times 1 is 2. Then we add 2. 4 plus 3 is 12. Carry the 1. We get 3. We have 2 decimal places, so 1, 2. It's 3.22. Okay? I'm going to show you how to use this logarithmic table to do the same thing, but instead of multiplying, we're just going to add. So we're converting what's 1.4 as a logarithm with a base 10. So I look at 1.4. Now the first column is 0.00, so 1.4 is just going to be 0.146. 2.3 it's going to be 0.362. So what you do is you look up the numbers, you write these down, and instead of multiplying, now you add. Carry the 1, we get 5. Then you look back at your table and you look for 0.508. 0.508 is right here. So if I look over, it's 3.2. And if I look up, look at that, 3.22. So what I have done is I have taken a number, converted it to a log, added the logs, converted it back. It's easier to add than multiply in general. So can you imagine very large numbers that are hard to multiply, 4 or 5-digit numbers by 4 or 5-digit numbers? What a pain. But if you can convert them to a log, and then add them, and then convert them back, why not, huh? And you might think, wow, that's not a very lot of numbers. I mean, I can't do a whole lot. Oh, this book here, this page of a book, this represents a page of many inside logarithm books. And they would do all kinds of numbers and all kinds of decimals. And you would actually flip through these books and find these numbers. And you would say, what a pain in the butt. Well, it was. But it was also the only way you could really, really multiply very large quantities of numbers together in a quick way. That's basically their principle, how they're used. So we're going to have 3 properties of logarithms. I'm going to base that on properties you already know. If I asked you to simplify that, x cubed times x to the 5th, x to the 8th, right? Because when you multiply with the same base, you add the exponents. Well, same thing with a log. if I take a log, doesn't matter what the base is, and I multiply two numbers together, I can break that up to being the same as adding those logs. And it works in the same principle as this up here that you know. When you break up a log, if you're multiplying it, you can add the logs, which means when you divide, guess what? Yeah, you subtract the logs. Just like if you were dividing, you would subtract the exponents. Because really what a log is an exponent. Okay? And the last property is if I have a number to a power. If I take the log of a number raised to a power. Well, when you raise the power to a power, in exponents, what you do with those two numbers, you multiply them. So I'm going to take this y and multiply it by this exponent, the log base a of x. These are your three properties: multiplication, division, power. Let's use them in the next 6 problems and see how it works. So I'm pretending that I've looked at these numbers up already. I've gone to my logarithmic table and I've discovered that if I look up 5, its log base 10 is 0.6990, which means 10 raised to the 0.699 is about 5. Remember, it's not exact. That's why I have little wavy lines there. It's approximately true. 10 raised to the 0.8451 is about 7. Okay. Let's use those facts and figure out the log base 10 of 35. So I can only use 5 and 7. How do I get 5 and 7? How do I use 5 and 7 to get 35? Well, yeah. It's 5 times 7. And the property says if I multiply, I can add those logs together. So I'm going to take 0.6990 and add it to 0.8451. Add those two together. That's what I get. Which means that 10 to that power is about 35. And let me see what it really says. I get 35.002. Pretty close. All right, how do I get 25 using a 5 or 7 combination? Well, 25 is just 5 squared. And because I have that power now, I can now bring that power down and multiply it. So this is 2 times 0.6990, which means 10 to the 1.398 is about 25. It's lower than that, which it should be, because 25 is lower than 35. Now this third problem, 7/5, that's also a low number. It's a little over 1. But if I'm dividing, then I can subtract those logs. 8451 minus 0.6990. Now I get 0.1461. So 10 raised to the 0.1461 is about 7/5. All right, that's how they work. Gonna do 3 more. 245. Of course, a little puzzle. Like, how do I get 245 from these? All right, well, if you break this down, it's 5 times 49. Oh, and 49 is 7 squared. So don't I just have 5 times 7 squared? Well, now I'll use my properties. If I'm multiplying, I can add. Oh, and if I have a power, I can bring that down and make it a multiplication problem. So when it really comes down to it, I'm taking the log base 10 of 5 which is 0.6990, adding it to twice the log of 10, I'm sorry, the log base 10 of 7, which is 0.8451. So if I do that calculation, 2.3892. So 10 to the 2.3892 is about 245. All right. So 175. Let's see, how does that break up? Oh, that's just 5 times, oh, even easier. Think of it as quarters. It's 7 25s. So same thing here, except now my square is going to be with the 5. It's 5 squared times 7. And if I multiply, I add. And I have a power, so I multiply. 2 log 10 of 5 plus log base 10 of 7. So I have 2 of these 0.6990s plus 1 of the 0.8451, 2.2431. All right, 175 is smaller than 245, so it should be a smaller answer. So 10 to the 2.2431 is about 175. And last one for now. 0.2. Well, 0.2 is 2/10. If you actually say it out, 2/10. Well, guess what 2/10 reduces to? That's right, it's 1/5. Now, how does that help us? Because can I write this as a power? It's 5 to the negative 1. So what can I do when I have a power? I bring it out in front. Negative 1 times the log base 10 of 5. So it's negative 0.6990. So 10 to the negative 0.6990 is about 0.2. You're thinking this whole time, why did I 0.6990? Why didn't I just make it 0.699? Well, all these are rounded to 4 decimal places, and sometimes the 4th decimal happens to be a 0. You know, we just keep it consistent that way. So if we round the 4 decimal places, these are pretty accurate. Let's see how accurate. I'm just curious. What's 10 raised to the negative 0.6990? 0.199986. It's not exactly 0.2, but it's darn close. So if you rounded it off to 4 decimals, you would get 0.2. So it's not bad. That's one way logarithms were used. In our next video, we'll be using logarithms to solve equations, and then we're going to show you an example of how we use it to measure earthquakes. Until then, see ya.